Welcome back, design junkies, to Mechanical Engineering Made Simple. Today, we're going to be exploring the unseen giants that really power our modern world. Yeah, we're diving deep into the incredible engineering behind these massive steel behemoths, pressure vessels. I bet you've seen these things, right? Just trundling down the highway, taking up multiple lanes, and you've probably wondered, where on earth is that thing going? But have you ever stopped to think about where it came from? These are truly the unsung heroes of industry, built to contain immense pressures and temperatures. So, in this explainer, we're going to follow their entire epic journey, all the way from a blank page to a towering, finished structure. So, how do you even begin to create something so massive and so strong? Well, it all starts with the design. And for a pressure vessel, the number one rule is brutally simple. It absolutely cannot fail. Now, the primary enemy isn't just the pressure trying to push out, it's actually the forces trying to crush the vessel from the outside. This can lead to a failure mode called buckling. The best way to think about it is crushing an empty soda can. It doesn't just neatly compress, right? It suddenly and catastrophically crumples. That's buckling. And that is exactly what engineers are designing to prevent. So how do they predict that soda can moment? They use this fascinating concept called the slenderness ratio. It's basically the relationship between the vessel's length and its radius. See, if it's too long and skinny, what they call a long column, it buckles super easily. But if it's too short and stout, it's strong but really inefficient and heavy. The real art of the engineering here is finding that perfect sweet spot right in the middle. Okay, so we know how to stop it from collapsing under all those external forces. But what's the most efficient design to begin with? To hold all that pressure inside while using the least amount of material possible. Well, mathematically, the perfect shape is actually a sphere. It holds the most volume for the least amount of surface area. The problem? Spheres are an absolute nightmare to manufacture. And that's why you see cylinders everywhere. They're just far more economical to build. The key then becomes finding that ideal length to diameter ratio, or LD ratio. And as you can see, that ratio changes with pressure. For lower pressures, a shorter, squatter vessel works just fine. But as that pressure climbs, you need a longer, more slender design to handle the forces efficiently. This is a great reminder that the design is so much more than just shape and size. It's a dizzying matrix of decisions. I mean, look at this flowchart. This shows the process for just one tiny aspect, material impact testing. Engineers have to account for literally everything, from temperature to shock loads, and every single choice they make sends them down a different path on this tree, all to guarantee the final product is absolutely, unequivocally safe. All right, let's move on. The vessel is perfectly designed to contain pressure. But now, this massive, heavy object has to be supported, either in a factory or out in the field. And believe me, how you hold it up is just as critical as how you build it in the first place. So how a vessel is oriented fundamentally changes the physics of the whole thing. You can see the two main approaches here. You've got a horizontal vessel that rests on saddles, and then you have a vertical vessel standing up on a base plate. And even if they're built from the exact same material, the stresses they experience just sitting there are, well, they're from two completely different worlds. Let's just focus on the horizontal saddle for a second. Imagine you're carrying a really heavy log on your shoulders. The log wants to sag in the middle, right? That creates tension on the bottom and compression on the top. It also creates this intense, concentrated stress right where it's resting on you. Well, that's exactly what's happening here. The vessel experiences what's called longitudinal bending, shear stress, and this intense circumferential stress right at the horn of the saddle. The math for these supports has to be absolutely perfect. A tiny miscalculation in where you place the saddle or how you reinforce the shell around it can lead to the entire vessel just collapsing under its own weight. There is literally zero room for error. Okay, so the blueprint is flawless and the supports are designed. Now comes one of the most visually dramatic parts of the entire process, getting this giant from the fabrication shop to its final home. Moving a multi-ton, 100-foot-long vessel isn't exactly a simple task. It's a massive logistical operation. We're talking specialized multi-axle transporters, detailed route surveys, permits, police escorts, and sometimes they even have to temporarily raise power lines just to get it through. And often the forces a vessel experiences during transport are far more severe than anything it will ever see in normal operation. This is especially true when it's being shipped by sea. On a calm day, it's just dealing with its own weight. But in a storm, Oh boy, the rolling and pitching of that ship introduce enormous dynamic forces. So just how extreme can those forces get? The answer is pretty astounding, plus 1.5 G. What that means is during a storm, the pitching of the barge can add a vertical force that is 1.5 times the vessel's own weight. Just imagine that for a second. The tie-downs and the vessel itself have to be strong enough to handle that incredible, violent load.
Rail transport? Well, that presents its own unique challenges. You can't just throw a vessel on a standard flat car. To handle the concentrated weight and, just as importantly, to clear bridges and tunnels, you need specialized cars. Things like depressed center cars or well cars that actually lower the vessel's profile, making the journey even possible.
So, the vessel has been designed, built, and has somehow survived its epic journey. Now it's time for the grand finale, the most nerve-wracking moment of all, the final lift. This right here is the moment of truth. It's a carefully choreographed ballet of cranes and rigging. It starts with the initial horizontal pick, then a tailing lift starts to rotate the vessel, and then comes the main vertical lift that slowly brings this giant to its final upright position. But this isn't just about lifting. It's about the physics of the lift. As the vessel rotates from horizontal to vertical, the stresses on its shell are constantly changing. And there's this one specific, heart-stopping moment, what they call the critical point, where the bending stress on the shell reaches its absolute maximum. Every single bit of design and planning has been about successfully and safely passing through that single point of peak stress. I mean, think about that. Months, sometimes even years of complex calculations, meticulous fabrication, and insane logistical planning, it all comes down to this one single, slow, and deliberate movement. And with that final, careful placement, the journey is complete. The unseen giant is now part of the landscape, ready to do its job for decades. So the next time you drive by a refinery or a large industrial plant, I really hope you'll see it a little differently. It kind of makes you wonder, right? What other hidden engineering marvels do we pass by every single day?